Hello, my name is Ioannis Zaras and I will be presenting my final project with the title Autonomous Mission Planning for Firefighting Drones. Let's begin with the motivation behind this project. It all starts with the increase in number of wildfires. Wildfires are becoming more common. Communities and ecosystems are threatened globally. Particularly in Greece, my home country, wildfires have become a common phenomenon, especially in the summer months. At the same time, shortages in firefighting staff hinder fast response. This is why firefighters and scientists have begun to employ UAVs and autonomous systems for surveillance and fire suppression. I thought that LLMs would be a great technological fit for such a task because agentic large language models have been proven to excel at function calling, and they should be useful at executing human commands on the field. The scope of this project was to employ agentic LLMs to translate high-level instructions from firefighters into sequential drone actions for firefighting tasks. I would have to create a simulated environment and connect functions with that environment and with the LLMs. The LLMs would have to decompose complex firefighting tasks, reason about resources, and adapt their plans based on environmental feedback. In the end, I would have to evaluate baseline and fine-tuned LLMs to examine prompt engineering techniques and parsing techniques. I started with creating the simulated environment. I built a simple 2D simulated environment in which our autonomous UAV could move and act on. The UAV was named Whirlpool for simplicity and for making it more approachable. I incorporated functions that employ sensor readings, for example, reading aileron condition, wind status, and battery levels, and function that enabled Whirlpool to detect fires, release its water payload, and move around. Everything was visualized using matplotlib for speed and simplicity. The architecture of my solution was to give access to the model via system prompts. So I listed all the available functions in the LLM's system prompt, and I also detailed instructions for how to generate its response and how to call the functions. 4 models were developed for this project. The first one was a base Qwen 2.5 model, no fine-tuning, nothing, just the model and a good system prompt design. The second model was a fine-tuned Qwen 2.5. The third model was a pre-trained Qwen 2.5 Instruct, so this model has been pre-trained to call function, and this is a non-conversational version, so just a single prompt and a single response from the LLM, no conversation. And the fourth version is a pre-trained Qwen 2.5 with conversational capability. So as we can see in the image on the right, conversational capability means that the LLM generates a response to the user prompt and prints narration. If the narration contains a function call, then the LLM receives the output of the function call and resumes generation. On the other hand, if the narration text does not include a function call, then the LLM waits for user reply, so we have a conversation. For the conversational models, this was the architecture, and we will see later on how this worked out. At this point, I would like to emphasize the challenges that come with utilizing LLMs for such purposes. I faced challenges that were related to an inability to call functions, which was proven to be a system prompt issue, which made the models believe that they cannot call functions. And I had to tweak the system prompt to tell them that to actually call a function, they just need to type it out in the appropriate format. Another issue was temperature sensitivity. Too low of a temperature, and the model struggles to do anything useful. Actually, it generates too little output. Sometimes it only generated the end of text token. Too high of a temperature, and the model generates hallucinated function responses and also struggles to adhere to the JSON format that the functions demanded to be parsed. Also, a very common problem was uncontrollable generation, meaning that the model was tasked with doing something and it continued generating output even after finishing its mission. Hallucinated function and responses, as I mentioned earlier, was also a problem that had to be faced. On the left here, we can see some dialogues, some conversations with the model that display exactly this problem. The first one displays an inability to call functions, and the second one is a great example of uncontrollable generation. The model was tasked with checking its battery levels and wind conditions, and the model ended up going to extinguish fires while the operator did not tell it to do something like that. Now, a word on the fine-tuned model. The fine-tuned model was fine-tuned on the glaive function calling dataset. We employed LoRa, low-rank adaptation, to effectively fine-tune the model. We used 10% of the glaive function calling dataset, and we found that one epoch and this percentage of the dataset was enough to actually have evident improvement. Regarding all of the models, I had to make the parsers lenient because sometimes the models struggled to adhere to the JSON format that the function calling demanded, and I used 0-shot, few-shot, and 1-shot system prompts based on the model, and stop words were used for all of the models to prevent uncontrolled generation. On the left here, we can see an example from the glaive function calling dataset. Now, on the right side, we can see Whirlpool extinguishing two fires. This is a GIF from the simulation environment, and the evaluation of the firefighting capability was as follows. 5 prompts were fed into each agent, each of the 4 agents developed. I present them here with increasing difficulty. 5 attempts for each of the 5 prompts. So I fed each prompt 5 times to each agent. I made a scoring policy which is as follows: 2 points for a successful mission, so 2 points if everything was done correctly, and 1 point for partial completion. And the partial completion is explained thoroughly in my report. The results were as follows. The baseline large language model, without pre-training, without fine-tuning, struggled with complex tasks and failed on the hardest prompt, even if I provided the prompt 5 times. Fine-tuning the model with a glaive dataset improved function calling consistency and reduced formatting errors by a lot, I should say. The pre-trained Qwen 2.5 Instruct non-conversational model performed even stronger in multi-step reasoning and planning tasks. And the best model overall was the pre-trained Qwen 2.5 Instruct with conversational capability, so with user feedback. Human in the loop was generally an improving factor for all of these models. No model achieved a perfect performance, but all of the models were able to solve some of the missions and succeed, and the conversational pre-trained agent was very close to achieving a perfect cumulative performance. Now, let's demonstrate a live experiment. Let's do a demo. I have my code here, so let's see. Alright. I will generate an environment where the drone has a battery of 27%, aileron condition is nominal, camera condition is nominal, the drone has a payload on it. I have placed some fires in my world. I have determined wind speed, wind direction, and starting position for my drone. Now let's start. Okay. Let's start with something simple like a greeting. Alright, hello there, I'm Whirlpool, your autonomous firefighting drone. How can I assist you today? No. Alright. Check for fires around. Report back to me. Let's see what it says. Understood, scanning the area for any signs of fire right now. It called to check stationary thermal cameras, and let's see if it will report. It reported back to me, confirmed, I'm detecting active fires at the following coordinates. Should I proceed to address these fires one by one, starting with the closest ones? Extinguish only the fire that is closest to you. Return to home afterwards. Let's see what it does. Understood. So it gets its current location. It finds its nearest fire, brings its avionics and motor on, and asks for my confirmation. I tell it to go and do it. It loiters over the fire. It sees that Whirlpool must be airborne to loiter, so it enables its motors. Oh, it enables its avionics. Alright, because motors cannot be powered on without avionics. Now it powers its motors. So actually this part here was a hallucination. The avionics on and motor on that we saw before was a hallucination. Nice. But now it's actually doing its stuff. It's it launched. Okay, now it's airborne. Alright. Will it loiter over the fire? Let's see. Yeah, it went to the closest fire. It's dropping the payload. Very nice. It dropped the payload. Let's see if it will return home. Heading back to home base. Great. Loaded home. Return to home base. Let's see if it will stop generation. Yep, it stopped generation. Very nice. Alright. Task complete. Mission complete, standing by. So that was a successful mission. We had some hallucinations, but overall it went okay. Let's continue. So, alright. So to conclude, instruction following LLMs demonstrated usability in the context of autonomous mission planning. All 4 models examined succeeded in some firefighting missions. The pre-trained conversational Qwen model, which we just saw in action, showed significant capability and impressive results. And when it comes to future work, we would evaluate newer Qwen models. Qwen 3.5 is out, and also Qwen 3.6 is out now. And we would expand fine-tuning with more epochs and specific domain data. So data related to drones or firefighting. Also, more advanced simulation environments with dynamic fire spread, wind, and realistic UAV constraints would also be an exciting way forward. So, a more realistic simulation. Thank you very much for staying with me in this presentation. Thank you.